start that. Taking video. If I minimize this, it'll turn off. So if I do that by accident, say something, but this will change if it turns off. So just watch it. Any questions on what we did Tuesday? I gave you some practice homework. Any questions on those? All right. So what I want to do is, we're actually doing most of chapter 5. I think if we can get it squeezed in. I've got to circle back to chapter 4. So let me just write this on the board. 4.5 and 4.6, I want to circle back to. I don't know if I listed that on D2L, but I'll put it on there. I'm hoping today we'll get to the stuff that I think is just a little more in depth. I'd rather do that today rather than Tuesday. So we did 5.3 last time. But at 5.3, there's one central concept for each of these sections. I want to hit all of them. 5.3 through 5.8. So 5.3, 4, 5, and we'll see how far we get. Wow, it seems like this is all. I want to be 5.9. 3, what is 4? So 4, we did chapter 4, the enthalpies of reaction. It was how you use this in a calculation. All right, so that's, this thing about enthalpy is a general statement, and the sort of details of how that works are what each of these chapters do. Did I do that right? 3, 4, 5, 6, 7, 8. All right. But I'm going to start with the one of these. So all of these are about details in how you get that energy change, the enthalpy change for a reaction. 6, 7, 5, 6, 7, 8. I'll cover those things. But I want to start with 5.8 because I think it's the one that really gives you the best idea of where that comes from. Let me just skip down to here. So that chart I gave you, in this chapter, there it is. So there's the start of the chapter, bond enthalpies. So the chart you have is this. It's here in the chapter and it's in the appendix. I'll give you this on a test. You don't need to memorize these, but this is what I'm going to describe, what those are. I think it's best to just start here. So sample exercise 5.12. All right, let me make sure the video is pointing where I want it. It's so good. All right. So that's showing you the molecular diagram. That could also be written like this. 1, 2, 3, 4, 5, 6. C2H6. Plus 7O2. So it's a combustion reaction. 4 CO2 plus some H2O. 6. All right. But that's the better way to see it. And I think since we haven't talked enough about molecules, that I'll have to show you these diagrams to do this. So I just wrote this to show you that this is something you've seen before, but this is really the way you need to see it to answer these types of questions. And then as in last Tuesday, I would go out here, delta H equals, minus some number. And so I'm going to show you the details on how this shows up. I already mentioned that you have to put energy in to break bonds, and then when bonds form, energy comes out. If you put 5 units of energy in to break bonds, and then 10 units of energy comes out, that's exothermic. But if you put 10 units of energy to break the bonds, and then 5 units comes out, that's endothermic because energy stayed in there. That'll be a little more obvious what's going on when I show you this. But it works like this, and I need one of these. All right. First of all, let me say, if I have 2 of those, so that's telling you just balance-wise, think of it as having 2 molecules like this. 2 identical C2H6 molecules. All right. What I need to do is break this down into the bonds that are there. 2 C2H6. So this is saying 2 of these, and there's 1, 2, 3, 4, 5, 6 C to H bonds. There's a C to H bond, C to H, C to H. This is what you need to hunt for on these molecules. That's C to C, so I'm not going to highlight it. But there's 6 there and there's 6 there. The way I would say it is 2 times 6. Or let me just do it like 2 times 6. That's how many C to H bonds are there. Can you see that? Does that make sense how I added that up? Okay. Let me erase this. So for each one of these, there's only one double bond, oxygen to oxygen. So I'll just say it's 7, or I could say 7 times 1. For the CO2, there's 4 of these, and there's 2 C to O double bonds. So I'll go 4, it's 2 of those bonds. And then H2O, there's 2 O to H bonds, and there's 6, so I'll go 6 times 2, and that adds up the bonds. Your book does this weird notation. The way I would notate this is I would go C to H bonds. And here I would go O to O bonds. I didn't leave enough room. Back that off. 7, 1, O to O double bond. And I just put it in quotes like this. 4, 2, C double bond to oxygen. 6, 2, and it's H to O single bond. I would do it like that, plus make this look neat, and then the arrow, and plus, okay. Notation-wise, do you see what I have here now? So looking at this chart, it's actually the first one. You can see it's C single bond to H. This font's a little weird, but can you see down here the C is a double bond to O? As long as you can see the difference between single and double bonds, this piece of paper will work. But that's telling you, I'm going to put in this parentheses, 413. You can see at the top it says kilojoules per mole, so that's the units we're in. And joules is the measurement of energy. Very frequently when you have a standard number for something, and it could be positive or negative, meaning
if I put 413 kilojoules into 1 mole of this, the bonds will break. When these bonds come back together, I'll get 413 out. So there is a positive and negative to this, but typically when there's a positive and negative, when they're tabulated, just the positive number is put in the table, because you add the positive, negative, depending on the context. But that's saying 413 joules per mole for this bond, but I do have to multiply it up like that. 2 times 6 times 413, that's how much energy goes in. 7, 1. So find the double bonded between 2 oxygens and tell me what the number is. You see it? 495. Now I'll put the arrow again. C double bond to O. You see it? 799. 4 times 2 plus 6 times 2. What do you see for H to O? Single bond.
463.
463.
Mm-hmm.
All right. Really, what I need here is I'm going to take the arrow away and I'm going to put large brackets here and a negative sign. What you get from all that, it's an estimate of the delta H. We could say delta H of reaction, but that's one way you can estimate this without actually going and doing the experiment. This, let me open this. There's calorimetry, Hess's law, enthalpies of formation and bond enthalpies. We're on bond enthalpies. That's a chart of bond enthalpies. These are really 4 ways to find the delta H. Calorimetry is the experimental way to do it. And these are 3 theoretical ways to calculate delta H. And that's where we're going. But the bond enthalpies, I think, is the most intuitive. So I started there. If you calculate all that, I'll just skip down here. You will find negative 2,856 kilojoules per mole. So now I could write for this delta H up here. I'll write it up here because I don't think y'all can see past the screen. But you get, what did I say, negative 2831 kilojoules per mole. In some sense, that's it from this chapter that I would say. That's how you estimate the delta H based on bond enthalpies. But that's sort of a mechanical way where all these bonds are the ones that have to be broken. So that's energy going in. So that's what you're calculating here between these 2 brackets, the energy going in. And then this estimates the energy that comes out when all those bonds form. So in this brackets, it's telling you the energy that comes out when bonds form. So bonds break. Energy out when bonds form. And that gives you the answer. And you still look here to decide whether it was endothermic or exothermic. They have this outline. So this is energy that goes in. This is energy that comes out. This number is bigger than this number, so this ends up negative. So it tells you on balance that energy goes out of the system, and this is exothermic. The negative sign is from the standpoint of the molecules themselves. So the molecules, the atoms and molecules involved have lost 2,831 kilojoules per mole in general. You follow that? All right. The problems for this, I'll put in a Word document for you. Let me. But I've got here for this section, there's a couple of these that I only want you to do A. You know how these have A, B, C, and D? 86, 87, 88, 89, and 90. 86. 86. But I might want to, so they give you the balanced reaction. I'll give you the balanced reaction. Any of these equations that don't have it, I'll add them to the Word document when I list these. Oh no, I crossed off 85 and 86. So skip 86, go to 87. '89 and 90 I've written down, do A only. So there's 4 of these. I'll leave that one so y'all can do it. Let's go to this one. This has an A and B. You can do both of these. Let me write them out. So you do have to look at the structure and sort of inspect what's going on. And what I just did, every single bond that was there broke. And every single bond that formed was a new bond. That's not always true. In this case, this bond breaks and this bond breaks, but these don't, so we don't have to calculate these. Do you see that these don't change? The C to Br. So those just won't go in our calculation. Nothing happens to them. C, bromine, bromine, H plus Cl, Cl, and it's C. So this bond breaks, this bond breaks, this bond forms, and this bond forms. So what we're doing here is, this balanced as it is, so there's no coefficients. So it's 1 to 1 to 1 to 1. So all we need then is, there's 1 C to H, 1 C to H plus 1 Cl to Cl. I mentioned this is the only time I've ever seen this notation. When I'm writing a C to H there, and y'all understood, I just replaced this with the number from that chart. So I would go, what is it for C to H single bond? It's the first one, isn't it?
413.
So I just write it like this, C dash H with the quotation marks. Your book does this. I don't even know why they use D. Your book writes it this way, so don't get confused. The only place in the world I've ever seen this. No other textbook, no other scientist I've ever seen do this. I don't know where they came up with it, but. You've got 1 C to Cl plus 1 H to Cl equals delta H. So this was 413. What is Cl to Cl? Is it on there?
242.
What is C to Cl?
328.
8.
H2Cl 431. I guess I'll calculate it, but from there it's just plug and chug. $413 plus 242. $328 plus 431. And this is going to come out negative. We get kilojoules per mole. And once you have that, you can do calculations like we did Tuesday. And that is an estimate. It's not going to be exact. There's a handful of details that can go into this. We won't cover those details until stuff for chapter 3. But most of the time they're kind of minor details, so they'll change this a little bit. Going up and down the stairs before class because I couldn't find one of y'all's tests. So I'm already sweating. But that's that section, bond enthalpies. Bond enthalpies added up can give you the overall reaction just by looking at the bonds. So that's that chapter. That section. Okay, and another way to do bond enthalpies. So I guess I'll back up and do 5.6, Hess's law. So an old school scientist came up with this, named Hess. So another way to figure this out. Another way to estimate delta H. If you have this reaction, and you have the delta H in hand, and then you've got another different reaction, and you have another delta H in hand, and now you have this third reaction that's kind of a sum of these two reactions, you can play around with these numbers to get the new the new enthalpy. This chalk dust. All right. You've got these two as reactants, and there they are. You've got this as a reactant, and there it is. These two as products, and they are there and there. You've got this as a product, and it's there. You could add those H2Os together to have 4 H2Os. That equation. Let me try another example. All right, let's do this one. So what is the delta H for this reaction? So what you'll do, the other one was just adding them up, so I didn't want to do it that way. All right, you start like this. You look at it and go, I have carbon on the left side. And you look down here and you look for just carbon, solid carbon. You see it here. Here, it's on the left side, so I want to use this exactly the way it is. C plus O2 makes CO2. I want H2 on the left side.
This one already has H2 on the left side, so I'm going to write it down the way it is. It's H2. I need to bring the coefficients along. Half O2 H2O. Oh, and I want to bring the numbers along. Negative 395.5. And negative 2.5.8. Okay, and I need C2H2. I need it on the right side. This one has it on the left side. So I'm going to swap this. I'm going to make these the reactants and these the products. So I'm going to write 2CO2 H2O yields C2H2 plus 5/2 O2. And then the number that goes with this one is this, but when you do what I just did and you swap it, you change the sign. So now I'm going to have positive 1299.6. All right. And now I'm just going to add up all the pieces. I need to have 2C, 1H2, and 1C2H2. And it'll work out if you do the math. Okay, over here, I have, how many C's do I need 2 C's, so I'm going to do this. I'm going to multiply through by 2 here, because I need 2 C's. I need 2. So I multiply through here and go 2, 2, 2, and I'm going to multiply by this by 2 as well. 2 times. All right, that'll give me 2C. I need 1 H2, and I have 1 H2. CO2 doesn't show up in here, but what you can do is there's 2 CO2 on the left and 2 CO2 on the right. These cancel. So I am almost literally adding up, but the way the rules go, if you multiply, then you multiply all the way across, including the number. And if the same thing shows up on both sides, you can cancel it. But I can only cancel these because it's 2 here and 2 here. What else? Is the H2O in the way? Yep. And there's 1 H2O here and 1 H2O here. Those cancel. If I add these up, 2 1/2 O2, and over here I have 5/2 O2. But that's what this is anyway. If you know your fractions, 2 times 2 plus 1 is 5. So you have to remember your what do you call it, perfect fractions or whatever. What do you call this, improper fractions? That's improper fraction. So this does equal 5/2 O2. I mean 5/2, yeah, 5/2 O2. These together added up. 2 O2 plus 1/2 O2 is 2.5 O2, which is 5/2 O2. You with me? Everybody follow what I'm doing? So what you get is, you cancel that and that as well. So those go away, and I'm left with 2C plus H2, and that's it. And so as long as you do all that right and you multiply when you're supposed to, 2 times negative 395.5. I'm just adding them up now. Plus 285.8 plus 1299.6 delta H of that reaction. Another way to estimate the delta H. It's a little involved. This takes some practice. But the rules are, if you have to multiply through by some number, then you have to multiply this. If you swap the reaction backwards, you change the sign. Did I change the sign? Yeah, the 1299, I changed the sign on. So that's positive 1299.6. I guess I'll calculate it. And then we'll scroll down to see if I made a mistake. $791. I guess I'd have to go 79, 791, 0. These are exact. These come from these coefficients. So I guess I have to put a 0 there. Negative 285.8. Oh, I'm not multiplying that? Yeah.